Welcome to section 4.4 in the Intermediate Algebra online lecture series. In this section, we're going to be talking about linear inequalities in two variables. We have looked at both linear inequalities in one variable and compound linear inequalities in one variable, in which we graph those on the real number line. Well, we can also consider inequalities that may have two variables, like an x and a y. Just like when we have equations in two variables, when we graph those are typically lines or curves in the plane. Well, now we're going to have inequalities. So instead of being lines or curves in the planes, they're going to be regions of the plane, separated by lines or curves. Now, since they're linear inequalities, it's going to be where we draw a line somewhere in the plane, just like we would graph a line that was an equation. But half of the plane then, either one side or the other side of the line, is going to be shaded, representing the entire solution set to that inequality. That is, everything on one side of the line or the other side of the line will turn out to be a point that satisfies the inequality. And that's what we're going to learn how to do in this section. The essential concepts for section 4.4 are as follows. We're going to begin by graphing a linear inequality in two variables. Then we're going to graph a system of linear inequalities. And of course, we want to be able to solve applied problems that use either linear inequalities in two variables or systems of inequalities. The basic approach for solving linear inequalities in two variables is by graphing. And what we will do in each problem where we're asked to graph an inequality, we have two different variables in there. We're going to graph them on the Cartesian plane. We start by replacing the inequality symbol with an equal sign and graph the corresponding linear equation. That is, treat this as though it were an equal and graph the line. But with one caveat, we're going to draw a solid line if the original inequality contains the or equal. That is, the bar underneath the inequality. And we're going to draw a dashed line or dotted line if the inequality does not include the or equal. And the reason for that is that if we have an or equal in there, that means when we replace this with an equal sign, that line is actually part of the solution, because or equal means the equals is also part of the solution. However, if it's less than or greater than, the equal sign replaced in here, which actually is representative of that line that we will draw, is not included in the solution set. The next thing that we do is we choose a test point. Pick a point in one of the half planes, that is, on either side of the line. Pick one. Okay, so make sure that it's not on the line, and you're going to pick just any point you want. You plug it in. So you substitute the coordinates of the test point into the inequality. If a true statement results, you're going to shade, color in, the half plane that contains the test point. If it's false, then you're going to shade the other side. Shade the side of the line that does not contain that test point. Okay? And then everything that's shaded is part of the solution set. That means if I pick a point in the shaded side, it will satisfy the original inequality. You will have graphed everything that satisfies the inequality. Okay? Now let's do this with this example here. Start by replacing the greater than sign with an equal sign and graph the line. You'll remember the easiest way to graph a line when it's in standard form like this is to use x and y intercepts. That is, I can pick 0 for y and I get x minus 0 equals 6 or x equals 6. Okay? Now, 6. And I can plug in 0 for x. 0 minus y is equal to 6. So divide both sides by -1. Y is -6. Now I have 2 points. I'm just going to plot those 2 points on my Cartesian graph here. So go over 6 and up 0, right there, and then over 0 and down 6 right there. Now I'm going to draw the line. Now I got to check, is it or equal to, or is it not or equal to? In this case it's not or equal to, so I'll use a dashed line. So just drawing a dotted line as straight as I can right there. Now either everything above the line is a solution to the original inequality, or everything beneath the line is. And the only way to figure that out is to choose a test point. Now my favorite test point is always the origin. As long as it's not on the line, that's the easiest one to plug in. So my test point is 0, 0. Substitute that in. Take 0 minus 0 and put that into the inequality and see if it's true or false. So that gives me 0 is greater than 6. Now is that true or false? Well, that's a false statement. So the side containing that test point is not in the solution set, which means everything else is. So all of this side, if I were to shade it, right, everything beneath that line shaded. That's my wonderful shading job that I can do with my pen here. That is the solution set, everything beneath here. Okay? That is how we graph the linear inequality. All right, let's approach this next one the same way. Start by rewriting the inequality as an equal sign problem. And I'll graph the line using my value table method. So I'll pick a 0 for y. That gives me 6x is equal to 12, or divide both sides by 6. I get x is equal to 2. All I did was plug in 0 for y. Now plug in 0 for x, I'll get a negative y is equal to 12, or y is equal to negative 12. So I will draw that line on my Cartesian graph, Cartesian plane here. So I need to go over 2 and up 0. Oh, what did I do wrong here? I plugged in 0 for x, right? And got negative 12. So 0 left to right and then down 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There it is. So I'm going to draw the line through there. Now is it solid or dashed? And I believe it's going to be solid, right? Because it's or equal to. So there's my line right there. Now is it to the left or the right of this thing? And so to figure that out, I pick a test point. Again, I need to pick something not on the line, and since the origin's not on the line, I'm going to use it, 0, 0. You get to pick whatever test point you want. Anything you want on the plane that's not on the line will work as a test point. So I get 6 times 0 minus 0 is greater than or equal to 12. Just plug it back into the original inequality. That gives me 0 is greater than or equal to 12, which is false. So I need to shade the side of the line that doesn't contain that point. If it had been true, I would shade this side. But since it's false, I'm going to shade this side. So everything on the line and in this shaded region satisfies that inequality. Any point, if I plug it in out of this shaded region, will satisfy that inequality. The next example, we can actually do this one almost immediately without any work at all. Whenever you see the inequality y is greater than or equal to 4, if I wanted to graph this on my traditional Cartesian system, right, I would just go to y is equal to 4. 1, 2, 3, 4. That's this horizontal line here. Remember, y equals 4 is always a horizontal line. And greater than or equal to 4, where are all the points with coordinates y greater than or equal to 4? It's clearly above that, right? Because greater than 4 means higher than 4, so it's going to be this region here. And it was a solid line because it was or equal to. Alright, so that one I didn't even have to choose a test point to figure out. Although I could have. It was easy enough to do without. This one can be done similarly. Start by drawing your Cartesian system and then graph this as an equality. That is, x is equal to negative 1. That's going to be here. And it's a dashed line because it's not or equal to, it's a strict inequality. And now if x is less than -1, that would mean everything on this side of that line and up to that line, but not including it. Okay? Fantastic. Now look here, we've got a system of inequalities. How would we go about solving or graphing the solution set to the system? Well, the trick here, all it is you graph both on the same graph, and the overlap or intersection is the solution. So it would start with x minus y equals 1, that is starting with the first inequality, and graph that using my technique of picking the x and y intercept. Plugging in y equals 0 gives me x equals 1, right? 0 here means x equals 1. Plugging in 0 for x, I get negative y is equal to 1, or y is equal to -1. So on my graph, I will go to point 1, 0, which is here, and 0, -1, which is here. I'll graph a solid line through there. I'm going to pick my test point, which is 0, 0, and say, is 0 minus 0 greater than or equal to 1? Is 0 greater than or equal to 1? That's false, so I would shade down here, right? Everything underneath that line is a solution to the original. Okay. Now what about the second one? We'll do the same thing. Start with x plus y is equal to -2 and graph it using your x and y intercepts. 0 for x gives me y equals -2, and 0 for y gives me x is equal to -2. Okay, so -2 here, -2 here, and it's a solid line, so it goes through these two like this. Again, I'm going to choose as my test point 0, 0. And say, is 0 plus 0 less than or equal to -2? Is 0 less than or equal to -2? Again, that's false, so I would not shade the side with that line on it, right? And looking at this line, I'm going to shade beneath it. Okay, so where is the solution to the problem? Well, it's everything that's shaded or included in both of these sets, which means this part of this line, this part of this line, and everything beneath these two. That is what's shaded in both sets. So there is your solution. Okay? Alright, let's look at this system. Now we've got 4 inequalities included. The first two are actually pretty easy. Let's start off by just identifying where they are on the Cartesian plane, right? And I'm going to make use of my highlight here. X greater than or equal to 0 means include the x-axis, right? And go which direction? Greater than. So everything over here is x is greater than or equal to 0. Okay? Y greater than or equal to 0 means include the y axis. How about I say this the correct way? It means include the x-axis, right? Because that's where y is equal to 0, and everything with a y coordinate above there. So all this. So what region are we talking about that has both of these true, right? So far we're up here in the upper right quadrant. Okay? Now let's look at this guy. Okay? Now I'm going to graph it the same way I did before. Take 8x plus 2y, set it equal to 16, get your x and y intercepts. Plugging in y equals 0 gives me 8x equals 16. Divide both sides by 8. I get x is equal to 2. If I plug in 0 for x, I get 2y is equal to 16. So divide both sides by 2, I get y is equal to 8. Okay, so over 2 here and up 8. It's right there. It's going to be a solid line. Right here. The question is, do I graph above it or below it? So my test point, I'll plug in 0, 0. That gives me 0 plus 0 is less than or equal to 16. Right? 0 is less than or equal to 16. That's true. So that means I will shade beneath here. Now what do I have so far that's my solution? Right? I have everything in this region right here. Right? Is shaded. Just that right triangle. So far, that's what my solution looks like. So this is the green region, right, for the green equation. Alright, we got one more equation, so I'm going to squeeze it in right here. Take 4x minus 3y, set it equal to 12. So that would be, if I do x and y intercepts, y equals 0 gives me 4x equals 12, or divide both sides by 4, I get x is equal to 3. Plug in 0 for x, I get negative 3y equals 12, or divide both sides by negative 3, I get y is equal to negative 4. So I go over 3, which puts me right here, up 0, and I go down 4. 1, 2, 3, 4. It's right here. There's my line. Test point, we can again use 0, 0. So plugging in 0, 0 into here gives me 0 minus 0 is greater than or equal to 12, or 0 is greater than or equal to 12, which is false. This test point's not in that half, so I'm going to shade beneath here, which means I'm going to shade down here. Or if I use my color, purple. Now the question is, do I have a region that's shaded by all 4 colors in all 4 graphs? Remember, up until this last equation, everything inside this triangle had been shaded by all 3 colors. Now everything purple is beneath here. There is no region on this graph that's shaded in all 4 equations. Okay? Now if there had been, that region would be the solution. But in this case, there is in fact no solution. Right? The solution to these 4 is the empty set. And that's the only way you can tell it, is by graphing all of them on the same graph and seeing if there is an overlap. In this case, because there's no overlap of all 4 of them simultaneously, that means there's no solution to that system. Now we finish off this section and this chapter with a word problem where we're going to be given a situation that we can model with a system of inequalities. We want to look at the region that satisfies the system. We have an elevator that can hold no more than 2,000 pounds. Fairly typical. If a child averages 80 pounds, or children average 80 pounds, and adults average 160 pounds, write a system of inequalities that models when the elevator holding X children and Y adults is overloaded. And then graph that system. So here's what we know. We got X equals the number of children, and Y is equal to the number of adults. Now, first thing I can tell you is that there is a restraint or restriction on what X can be. First of all, X has to be greater than or equal to 0. You're always going to have at least 0. You're not going to have a negative number of children. And the same thing for Y, greater than or equal to 0. Just like we had in the last example, those two start off with our number 1 criteria, is that these 2 variables are positive. Now, if x is the number of children, y is the number of adults, what's the weight for x children and y adults? Well, we know this. The average child weighs 80 pounds. So if I have x children, their weight is going to be 80 times the number of children that we have. Okay? Plus the weight of the adults. And if we have y adults that weigh 160 pounds each, okay, or average 160 y. So these are our first two equations in the system, and the last one would be that 80x plus 160y needs to be, or can be, no, well, I guess to say it this way, we want to know when it's overloaded. It's overloaded if that's bigger than 2,000. Okay? Obviously, we have to have a positive number of children, a positive number of adults, and the weight is going to be over 2,000. That's when we're trying to find. We're trying to find when this thing is overloaded. So to graph these, we'll do the same thing we did in the last section, or in the last problem, and graph them all simultaneously on the same Cartesian plane. So the first thing I know is that from this, x greater than or equal to 0 means I'm over here, or on the line. What I know from the second equation is that I'm either on the x-axis or somehow above it. So that means I'm somewhere in this upper right-hand quadrant. Now, where am I in there? I'm going to graph this equation right here, or this inequality. So take 80x plus 160y greater than 2,000, so treat it as an equals first. Graph that line using x and y intercepts. If I plug in 0 for y, I get 80x is equal to 2,000. Dividing both sides by 80, x is equal to 250. If I plug in 0 for x, I get 160y is equal to 2,000. Divide both sides by 160. I get y is 12.5. Okay, so on my x-axis, let's go, since I got to go up to 250, let's go in increments of 50. 50, 100, 150, 200, 250. There's that x-intercept. And let's go units of 10 on the y-axis. 10, 20, so 12.5 is roughly right there. Okay, now I will graph this with a dotted line because of the or equals not included there. So I'm going to just do a dashed line. If I can get it to go straight here through there and back up this direction. Now the question is, do I shade above there or beneath there? So I plug in my test point using the origin again. If I plug in 0, 0 in here, I get 0 plus 0 is greater than 2,000, or 0 is greater than 2,000, which is false. So I don't shade the side that contains the origin, I shade above. Now the regions that's shaded in all three equations, or sorry, all three inequalities, is the solution to the problem. That's when the elevator would be overloaded. So what region is that? Well, let's draw it with a green line here. It includes this line. Okay, it doesn't include this, but it includes the x-axis this way, and everything over here above the line is the solution. Okay. Color that in nice and pretty. Doesn't shade down here, by the way, right? Because it's got to be positive in the y coordinate. So right down to there, not including that line, touches it and then follows along the x-axis. Alright, so any point in this region, it would be overloaded. And we graph the solution set. And that's it. That's the end of section 4.4 and the end of chapter 4, what we're going to be doing with inequalities in this course.